Okay, I'm looking at an additional example here of using equilibrium and equilibrium constant expression to solve a problem. We want to look specifically at what happens when we end up with a little more complicated system once we plug some x's into our ice chart. So in this case, we have a 1 liter flask. We've got 1 mole of hydrogen gas, 2 moles of iodine gas, right, at a particular temperature. So equilibrium constant is temperature dependent. So at this little bit higher temperature, we get a different value for this equilibrium constant than we saw in one of the past problems, even though it's the same reaction. We're given that equilibrium constant along with the reaction. We want to figure out what are the concentrations of the components here when we get to equilibrium. So 1 liter flask, that's helpful because that means moles and molarity are going to be the same. But we do want to start with an ice chart here. So let me recopy the equation so it's all nice and arranged on the same line. And we want to start to fill out our ice chart here to go along with it. Now, hydrogen is 1 mole. Iodine is 2 moles, and not just moles, molarity is important here in this particular case as well. The concentration of the product, though, would be 0 under the initial conditions. So like we saw in the last problem, right, in this case, we want to use some sort of variable like x to figure out what the change is going to be and how that's going to affect the concentrations by the time we get to equilibrium. So if I use minus x for hydrogen, right, we know the reaction is going to have to shift. It's going to have to fill in this 0, and there'll be some positive value for the concentration of HI at the end. If hydrogen changes by x, then iodine will as well. Every time a hydrogen reacts, an iodine has to react as well. And taking into account the 2 here, the increase in the concentration of the product would be 2x. Now what this gives us is at equilibrium, hydrogen would be 1 minus x, iodine would be 2 minus x, and the concentration of the product, hydrogen iodide, would be 2x. Now if we plug this in to our equilibrium constant expression, again K here is going to be based on that reaction. It's going to be HI concentration squared over H2 and I2. Plug these in. In fact, let's plug in our value for the equilibrium constant as well. That's 50.5. And HI is 2x, so up on top here we'll have the quantity 2x all squared. Down on the bottom we'll have 1 minus x times 2 minus x. Okay. Now what's different here from the last problem we looked at is the 2 quantities down here are not the same. So we can't think of this as a quantity squared, which allowed us to simplify all of the other pieces of the formula. This is going to end up having an x squared term, an x term, and a numerical term in our equation. And that means this is a system where we're going to need to use the quadratic equation here to solve for x. So what we need to do with this equation is get it in the correct form to plug into the quadratic formula. Okay, and we'll do that together. And then I'm going to kind of skip over the quadratic formula. But let me talk a little bit more about that when we get there. So the first thing I want to do is multiply out these quantities in the denominator and also in the top on the numerator of that equation. So 50.5, I need to square that 2 and make that 4x squared. Now, you would be surprised how often that's where people go wrong, is they take 2x squared and they don't square the 2, they just square the x. So make sure you square any numerical coefficient in there as well. Down at the bottom here, I would use the FOIL method. It's been a long time since I had high school algebra, so I don't know if that's still what they call it, but first, outer, inner, and then last. And that would give me 2. So 1 times 2 would be 2. Outer would be minus x, inner would be minus 2x. So if I combine those, that would be minus 3x. And then minus x times minus x would be x squared. Now I want to multiply everything in the denominator here by both sides of the equation. So I'll cancel it out on the right. It'll end up on the left. So 2 times 50.5 would be 101, minus 3 times 50.5 would be 151.5, and that of course is times x, and then x squared times 50.5 would be 50.5x squared. That's all going to be equal to 4x squared. Now, the form you want to plug into the quadratic equation is you want 0 on one side of this relationship, and then you want your other terms on the other side, and that's how you'll pull out a, b, and c. So I'm going to put the 0 on the left here. That's just the form I'm used to seeing it. You could do it either way as long as you're comfortable with where a, b, and c are going to come from. So if I subtract 50.5 from each side, I'll have 0. And then over here, this would be minus 46.5 times x squared. Add 151.5 times x to each side, so plus 151.5x. And then I'm going to subtract 101 from each side as well. And this is the form that I want for the quadratic equation. In fact, in this case, this value right here would be the variable called a, the x squared term. This value here would be b, and this value here would be c, the numerical term. You could plug these into the quadratic equation. Some of you may have a calculator that can do this for you. That is perfectly fine. And if you don't want to use a calculator and you don't want to spend the time plugging into the quadratic formula, you can find quadratic solvers online that generally work pretty well. You need to be careful of making sure your roots make sense, because some use approximations that don't actually solve the quadratic formula. So you can usually tell because your answers wouldn't make any sense. And in fact, we'll have to talk about that a little bit, because one of the roots is not going to make sense when you solve. You get 2 roots from your quadratic equation. Only one generally will be a proper answer to the problem. So I'm going to skip over that part. You had to have algebra to get into Chem 1, so I assume you guys can all do that from here once you get to this part of the equation. So if you do solve this, the 2 values you get for the roots of x are 0.935 and 2.32. Now, looking back at the beginning of the problem, right, 2.32 clearly cannot be the correct solution we're looking for, because if we take 1 and we subtract 2.32, that would give us a negative concentration of hydrogen when we get to equilibrium, a negative concentration of iodine when we get to equilibrium, and a negative concentration just isn't possible. So this root is spurious. It is a solution to the mathematical equation, but it is not physically possible for our particular problem, and that means this is the correct root, right? Oftentimes you'll get a positive root and a negative root. In that case, the negative root is spurious. The concentration of the reactants can't get higher by subtracting a negative amount, because there would be nowhere for that material to come from. So if this is the correct solution, now we're back to establishing what these concentrations are based on applying x into the system here. So the concentration of hydrogen would be 1 minus what we determined for x there, and that would be 0.065 molar, and that's not too hard of a subtraction. I don't think I need to pull out the calculator for that. Same is true for I2. 2 minus x would be 1.065 molar, and for hydrogen iodide it would be 2 times x, from back in our ice chart. So 2 times 0.935 would be 1.87 molar. In fact, 3 decimal places for most of our data, so this one can probably go to 3 decimal places as well. Okay, so a good thing to think about, right? So those are our answers, but a good thing to think about here is there's kind of a built-in check you can do here. You can take these values, plug them back into the equilibrium constant expression, and if these are correct, then you should regenerate K here. And in fact, in this case, I've tried that out, and you get within, I think it comes out to be about 53. So that would be a good thing to try on your own. Plug those back in and make sure that this solution is correct. And same thing when you're doing the problem. You can always kind of double check, because you have that equilibrium constant expression, to make sure your numbers make sense.